Hello everyone, this is Dr. Zach, and today we are going to define sequences and determine whether or not they converge. For our lesson preview, you're going to write a function f of n that creates your given sequence. So a sequence is a collection of ordered numbers whose domain is a set of positive integers n. For this first question, I want you to start with n equals 1 and determine f of n that makes this sequence. Similarly, work on the second question. Determine your f of n that makes that lovely sequence. So a sequence is a collection of those ordered numbers. The terms are going to be listed as a sub n, or A1, A2, A3, A4, and n is describing your domain, which starts at n equals 1, then 2, then 3, then 4. So for example 1, if we list the terms of the sequence, we want to think about what happens when you have n is 1, then n is 2, n is 3, n is 4. When n is 1, our first answer is -2. I hope you're better at drawing those than I am. When n is 2, we get a +4. The third term is -8. The fourth term is 16. The fifth term is -32. As you can see, this sequence is a list of alternating numbers. When I look at example 2, we're listing the terms again, defining a factorial for us. So when n is 1, 1 gets substituted in, and it's 1 times itself, which is 1. For our second term, we want to work out 1 times 2, and that gives us a 2. The third term, 1 times 2 times 3, which is 6. Fourth term, 1 times 2 times 3 times 4, which is 24. Take that answer, multiply it by 5, and you have 120. Please notice, if ever you see 0 factorial, that's defined to be equal to 1. So 0 factorial does equal 1. So some sequences are called recursive, or they depend upon the previous term. If you have a recursive sequence, you need to have one or more of the first few terms to determine the sequence. So for example 3, we're to list the terms again of our recursive sequence. Given d sub n is the name of this sequence. d1 is 6, d of n plus 1 is going to be written as 2d sub n minus 1. So our first term, d1, that's 6. Our second term is going to be equal to 2 times the last term minus 1, which is going to be equal to 11. The third term is going to be 2 times 11 minus 1, which is going to be equal to your 21. Then the fourth term, we're going to have 21 multiplied by 2 minus 1, which is 41. So you can see that d sub n is going to be 6, 11, 21, 41, and the next one is 81. So these are the first 5 terms of our sequence. So now we're going to graph this by hand. A sub n is 2n minus 1. We need a list of values that we're going to be graphing. So starting out, our first term is going to be 1. The second term is 3, or the next term is 7. So we're looking at the powers of 2 and subtracting 1 from each. So we have the first 5 terms. Now when we graph these, it's actually a discrete graph. We'll have the n going across, and then we'll have the values going up and down. So we 1, 2, 3, 4, and 5. Now my values are going up to 30, so I'm going to count by sixes. 6, 12, 18, 24, and here's 30. So when n is 1, the answer is 1. When n is 2, the answer is 3. N is 3, we're going to go up to 7. N is 4, we'll go up to 15. And when n is 5, we're going to go all the way up to 31. This is a discrete graph. Do not connect your dots. Sequences are discrete. For example 5, we're going to pull out our calculator, so get your calculator ready, please. First, we should be in sequence mode. So go ahead, change the mode, choose sequence, and go to y equals. Notice we have a different setup. The function that we are going to graph will be n divided by our n plus 1. Close your parenthesis, and if you look at your table of values, you can see that we have the numbers we were expecting. You can also graph these. So if we go to your graph, so I'm going to hit second, graph, and you can see that we have the values displayed on the graph. If we were to hit trace and walk along these values, you can see that the n, x, and y are all displayed as you walk through the different values. Go back for a minute to your y equals. Notice that your n min is set equal to 1, and u of n is n divided by n plus 1. Now let's look at our recursive problem. For the recursive problem, we're still going to start at the minimum n value is 1. We are using the function, the sequence 2 times, and then we want to have d sub n minus 1. So let's clear what we have and fill in the 2. When we choose the u value, we want to get the function before. So go ahead, and u is bound on the 7, so hit second, 7, draw parentheses, put in your n, and we want n minus 1, because we want the term before. Close your parentheses, so it's using function notation, and we will subtract 1. Now for this type of problem, we have to fill in u1, which is our first value, and the first value is 6. Once you have your function in, go ahead, look at your table. The table of values is given to you. These are the values that we were expecting. You could also, again, look at your graph. And what you should notice about the graph is you only see one dot. So we're going to have to zoom and choose zoom fit. So zoom fit, we should then be able to see more of our sequence. Again, if we hit trace, trace will walk us along the different terms in our sequence. Head graph number 2. Converge or diverge? That is the question. So our sequence A sub n is said to converge if the limit of your sequence approaches some value of L, and it's got to be a finite value. Now notice that when you're talking about terms, that is discrete data that's going to be bouncing up or down, or it could even follow a particular path. And if you can find a number L for which that path tends toward, then you know that your sequence is going to converge. Let's take a look at example 6. We're to find the limit of this sequence. In order to find the limit of that sequence, that means we want to determine the limit as n goes to infinity of a sub n. Now, because of the exponent, we're going to rewrite our problem as y equals 1 plus 1 over n raised to the nth power. Then if we log both sides, the natural log of y is going to be equal to n times the natural log of the quantity 1 plus 1 over n. And now we'll find the limit. The limit as n goes to infinity, the natural log of y is going to be equal to the limit as n goes to infinity, n times the natural log of 1 plus 1 over n. And when you do your substitution for positive infinity, you get an infinity multiplied by natural log of 1 plus 1 over infinity, so that's going to be 0, which is an indeterminate form. In order to use L'Hopital's rule, we're going to have to rewrite our problem. We have the limit as n goes to infinity of 1 over 1 over n, and the numerator will stay the log 1 plus 1 over n. Now we have 0 divided by 0 and can apply L'Hopital's rule. So we will have the limit as n goes to infinity for the numerator 1 over 1 plus 1 over n times 1 over n squared with a negative, and your denominator is negative 1 over n squared. Isn't it convenient that these will cancel out? Now, the limit as n goes to infinity. 1 divided by 1 plus 0 is 1. So we now have the limit as n goes to infinity of the natural log of y. Wait a minute. The n is not affected, so we have the natural log of y is equal to 1, or y is going to be equal to e to the first power. So what do we know? We know that the limit as n goes to infinity of the sequence a sub n is equal to e. So we are definitely converging, and we're converging to the value of e. For example 7, we're looking for the limit as n goes to infinity for our sequence b sub n. So that will be the limit as n goes to infinity, n plus 1. That answer, of course, is infinity. That means that the limit does not exist and if the limit does not exist, we know that b sub n diverges. So the limit of a sequence, let L be your real number, let f be a function of a real variable such that the limit as x goes to infinity of f of x is equal to L. If a sub n is a sequence such that f sub n is equal to a sub n for every positive integer n, then the limit as n goes to infinity of a sub n is equal to L. So here's what essentially is happening. If you can write the function and each one of your dots or terms falls on the function, if the function goes towards a limit, then your sequence will also go towards the same limit. And that will make things easier for us if we think of these as functions. So find the limit of the sequence. To do that, let us find the limit as n goes to infinity of n divided by 2n plus 1. So even though this is a sequence, which is discrete data, we're going to follow the same ideas for solving this limit problem that you did in Unit 1 for AB Calculus. You're going to drop your lower order terms. You're left with the limit as your n goes to infinity, n divided by 2n. The n's cancel out, and you have 1/2. So this sequence converges, and it converges to 1/2. All right, so now give questions 4, 5, 6, and 7 a good try. I'm going to share the answers with you for question number 4, question number 5, question 6, and question 7. Make certain you verify these answers. Next, we're going to discuss two theorems specifically related to sequences. Our first is the squeezing theorem. If we have a sub n, which is converging to some value of L, so we're going to converge to L, and a sub n is less than or equal to b sub n for the terms for all of their terms, and that also converges to L, then if C sub n is trapped between both of these sequences for a certain set of n values, then the limit as n goes to infinity for C sub n also must be L. So the sequence C sub n is squeezed into converging to L. So that's our squeezing theorem. Next, we have a definition for a monotonic sequence. So a sequence A sub n is monotonic if its terms are non-decreasing. So non-decreasing is kind of interesting. You have your A1 less than or equal to A2 less than or equal to A3, and that's going to continue. Or if the terms are non-increasing, so it's one or the other. Now, why it says non-decreasing, non-increasing? It is possible that some of the values are equal before they continue to either increase monotonically, or perhaps you have a sequence that's going to decrease monotonically, but a few of their terms are equal. So to be monotonic, your terms are going to be non-decreasing, non-increasing. Let's check out an example. Example 8, determine whether the sequence converges. Ooh, all right. So we could tell if it's converging if we're able to trap it between two other sequences. Let's first get an understanding of what S of n is doing. So let's write out a few of the terms. Do you notice that the sequence, after we write out a few terms, is always less than or equal to 1 over n? So if we have n is 1, n is 2, n is 3, for each one of these values are going to be less than or equal to 1 over n. So let's let b sub n equal 1 over n. And do you notice that each one of these is greater than 0? So let's let a sub n equal 0. All right, and we call this one, of course, C sub n. So what have we done? We know that a sub n is less than or equal to S sub n is less than or equal to B sub n for all n values, isn't it? So for all n greater than or equal to 1. How does that help us? If we find the limit as n goes to infinity of a sub n, that answer is 0. If we find the limit as n goes to infinity for b sub n, that is also 0. And from the squeezing theorem, that tells us that the limit as n goes to infinity for our n factorial over n to the n must also be equal to 0. So this one does converge, and the sequence converges to the value of 0. Let's discuss whether some sequences are monotonic. So, taking a look, let's write out a few of the terms of this sequence. We'll have 1 over 2 and 2 over 3, 3 over 4, and it continues, of course. Now, do you recognize that each of these fractions is slightly increasing? We might have a monotonic sequence. Saying it looks like they're increasing, though, does not prove that it's increasing. So we're going to rewrite S sub n as a function, because you know how to determine whether functions are increasing or decreasing by finding derivatives. So find this derivative and simplify. So we have 1 over x plus 1 quantity squared, which is always going to be greater than 0. And if it's greater than 0, we know that f of x is increasing. So that tells us that S of n is monotonic, and it is monotonically increasing in this case. All right, B sub n. For this one, we can't find a derivative. Let's write out a few terms, see what's happening. We will get e to the first power divided by 1 for our first term, e squared over 2, e to the third over 6, and then e to the fourth over 24, and of course this will continue. So it looks as if these values are decreasing, but I'm still not certain. What if we were to do a little bit of division? B sub n plus 1 divided by b sub n. If we think about that ratio, if we take the next term divided by the term before it, what's going to happen? If we're always decreasing, we should get a number that is less than 1. So let's see what happens. We have e to the n plus 1 over n plus 1 factorial divided by e to the n over n factorial. This is a complex fraction. Those are just roots. So let's rewrite it. E to the n plus 1 over n plus 1 factorial is going to be multiplied by the reciprocal n factorial over e to the n. Clean this up just a little bit. Let's see what happens. We will have e to the first power. Think about n factorial for a minute. So n factorial means n times n minus 1 times n minus 2, and it continues, whereas n plus 1 factorial is n plus 1 times n minus 1 times n minus 2, and that also continues. So cancel out the like terms, and we have e, which is a number, divided by n plus 1. And as n increases, this will go to 0. Therefore, we know that since this is going to 0, we're always going to be less than 1 for n greater than or equal to 2. Now, let's think about how that helps us. If it's always less than 1, that means that this is a monotonically decreasing function for n greater than or equal to 2, but that, which is just fine. We can still say we're monotonically decreasing because our original theorem said that n's had to be greater than or equal to some certain value, and in this case it's 2. Looking at example 11, we want to know if this is monotonic. So we're going to write out the sequence c sub n just to get an idea. When n is 1, we have negative 1. 2 gives us 1. 3 gives us negative 1. So as you look at this, I think we can firmly state not monotonic. Now let's put it all together. Our next theorem, if our sequence a sub n is bounded and monotonic, then it converges. So if we can show that there's an upper bound and a lower bound on the following functions, as well as monotonic, then we can say they're convergent. Let's take a look at example 12. We know from our prior work that it is definitely monotonic. Now let's see if it's bounded. We're starting at 1/2 when n is 1, but we're never going to get up to 1. So each term is going to be bounded by 1/2 and 0. So each term, s sub n, is going to be trapped between 0 and 1/2. So it's bounded and monotonic. Because it's both, we know that this sequence will converge. For example 13, we know from e squared over 2 is slightly bigger than e. We know from our prior work, though, that it is monotonic. Each of these is decreasing, so we can take b sub n and say that it is bounded between less than or equal to e squared over 2, that's your greatest bound, and 0, which will be your smallest bound. So it, too, is bounded and monotonic, therefore it must be convergent. For number 14, this one was not monotonic. It is bounded, though. For each one of these values, negative 1 is, we could write less than or equal to c sub n, and is also less than or equal to 1. So it's definitely bounded, but it is not monotonic, and therefore it is not convergent. We did a lot of work today. Make certain that you understand the concepts for convergence and divergence related to sequences. And just in case you needed it, the answers to your lesson preview have been provided. Have a great day.